So now let's continue with our discussion of quantifying variability. And we'll start with an example calculation. It is somewhat of an artificial calculation because we will have a fairly large number of measurements, in this case, n equal to 20 measurements. And the measurement number is in the first column. And in the second column, you have the actual values of measurements in units of parts per million, presumably of some kind of a gas or vapor. And these are denoted as x sub I. And the I refers to the ith measurement. And the measurements are 0.75, 1.53, and so on. In the third column, we have the natural log transformation of these measurements. And as you can see, these can, depending on the value of the measurement, these can potentially take negative values as well. So if you take these yi's, the log transformed measurements, and you sum up all these values, so at the bottom of this table you see a y bar, which is essentially the arithmetic mean of the log transformed values. So you sum up all the yi's and you divide by the number of measurements, and you get y bar is 0.169. In the bottom of the slide, you see if you can take the exponent of this 0.169, you get 1.18 parts per million. And this is the geometric mean of the distribution from which you have obtained 20 measurements. Now we can go on to the fourth column of numbers. So now we're trying to find out the standard deviation of these log transformed values. So yi minus y bar squared. So from each one of these yi's, you subtract out y bar, or 0.169, and you square it. And so that's the value for each row in the fourth column. And then you sum up these squares, and you divide by n minus 1, and then you take the square root of this whole quantity, and you get the standard deviation, which is 0.868. So this is the standard deviation of the log transformed values. And then if you go to the bottom of the slide and you take the exponent of 0.868, that will be the geometric standard deviation, and it will have a value of 2.38. So as you can see, the geometric mean, μs of g, is still in the units of the measurement. So it's 1.18 parts per million, but the geometric standard deviation doesn't have any units. It's a dimensionless number because, like we discussed earlier, it is considered as the ratio of the 84th to the 50th percentile of the values. And so therefore, there's no unit to this number. And so this is one straightforward way in which we can calculate the geometric mean and geometric standard deviation. But there is another way, and this is an important way to not only calculate the geometric mean and geometric standard deviation, but also look at the distribution itself as a whole. And this is by constructing what are called log probability plots. And it is essentially a plot of the cumulative exposure distribution. And we'll talk about how we do this in the next slide. But we obtain the cumulative data, and you plot the cumulative percentage of measurements less than a given value on the y-axis and the exposure value on the x-axis. The x-axis is logarithmic, and the y-axis is a probability scale that is compressed near the 50th percentile point and expanded near both the tails. And the one very important and very useful property of such log probability plots is that if the distribution of data are log normal, then your cumulative plot is going to be a straight line. So let's first construct a cumulative distribution table that we can then plot. I'm using the same data points as I showed in the table previously, except now they are rank ordered, meaning they are sorted in ascending order from the smallest to the largest value. So the first column is called rank order, and it ranges from 1 through 20, 1 being the lowest and the 20 being the highest rank order. The second column, rank ordered measurements in units of parts per million. So the smallest value in my 20 data points is 0.32. The next highest is 0.33, all the way up to the highest measurement of 7.43, which has a rank order of 20. The third column is the cumulative percentage, and this is 100 times the rank order divided by n plus 1. And so here n equal to 20. So for a rank order of 1, the cumulative percentage is 1. So rank is 1 divided by n equal to 20 plus 1. So 1 divided by 21 times 100, so that's 4.8%. And the highest value is 95.2%. The reason why we don't go all the way up to 100% in the cumulative percentage is we can never be sure from a finite sample that we would capture all the values in a log normal distribution. So we can at best be confident that a rank order of 20 probabilistically captures 95% of the values in the distribution. And hence we have the n plus 1 in the denominator rather than n. So the way to interpret this table is as follows. 4.8% of the distribution of exposures is less than 0.32 parts per million. 9.5% of the exposures are less than 0.33 parts per million. And going to the bottom of the table, we can say that 95.2% of the exposures are less than 7.43 measurements. So that's the way to interpret a cumulative percentage distribution. Now let's plot these data points on a log probability axis. So what I'm showing here is what is called a log probability plot. And on the x-axis, we have the concentration in parts per million, but it is a logarithmic scale. And it ranges from 0.1 to 1 to 10. So each big unit in the scale is a factor of 10. And on the y-axis, we have what is called a probability scale or a probit scale. And if you can see the units of this, they are more compressed near the 50th percentile point and more stretched out near the ends, both near the 1 to 2% and near the 95, 98, and 99 percentile points. So if you take the first data point, which was 0.32 parts per million, and you can see that this is the smallest value that is being plotted here, and that corresponds to 4.8% on the y-axis. And you can see that particular point over there. Likewise, if you go to the other extreme, we see that value of 7.43 corresponds to around 95%, and all the values in between. And even visually, we can see that these measurements follow a nice straight line, which indicates that the data come from a log normal distribution. Why is this better than just the brute force calculation that we did earlier of geometric mean and geometric standard deviation? So we know that the geometric mean is the 50th percentile of a log normal distribution. And so we can go on the y-axis to the 50th percentile mark and find the corresponding point on the x-axis that corresponds to the 50th percentile. And that is roughly 1.2 parts per million. If you recall, we had also calculated it exactly previously, and we got a number of 1.18 parts per million. So the visual approach is a lot easier to do. Plus, you get the added benefit of seeing the full distribution. Similarly, we can also calculate the geometric standard deviation, which is the ratio of the 84th to the 50th percentile. So if we go to the 84th percentile, which is conveniently marked for us in the log probability plot, that corresponds to 3.1 parts per million, and the 50th percentile is 1.2. So the ratio of those two is 2.6. And so that is the geometric standard deviation. So just in a very quick visual manner, we have obtained a value of 2.6. If we did a more precise calculation, we would get 2.38, as I showed earlier when we did the brute force calculation. So the added benefit of doing these calculations on a log probability plot is that not only do you get these parameters, you also obtain an understanding of the full distribution of exposures, and you can read off other percentiles that might be of interest, such as the 95th or the 98th percentile or the 99th percentile. So these are all going to be of use as we move forward in our discussion of exposure variability. What I'm showing in this slide are two graphs. The top part of it is our now familiar log probability graph, and this is reflecting the exposure variability in our similarly exposed group of workers. It has this characteristic skewed shape, and on the x-axis you have the exposure value, and on the y-axis you have the probability density function. And this reflects the overall variability, meaning that it incorporates both the within and between worker variability within this group of workers. The bottom graph actually shows the measurements from which the log normal distribution was inferred. And here I'm showing 8 measurements, and you can see that the exposure values range from slightly less than 4 all the way up to close to 16. And you can see that these numbers jump around. And so there is significant variability from one measurement to the next. And this reflects the variability in the workers' exposures. But in addition to this, you will see for each of the data points, there is an uncertainty around that. And this reflects the sampling and analytical variability around each individual measurement. And this uncertainty arises from the measurement technique that we used and the analytical technique that we used to analyze our samples. The main thing to note is that the sampling and analytical variability is much, much smaller than the overall variability in the measurements. That's the key thing to remember. The next slide, we show the relationship between the magnitude of sampling and analytical variability and the total environmental variability or worker exposure variability. And this graph is from a paper by Nikas et al. In 1991. What it shows is on the x-axis, the geometric standard deviation of the environmental variability or worker exposure variability. And it ranges from a GST of 1, which is the smallest value that the GST can take, all the way up to 4. And on the y-axis, you have a ratio of analytical variability to total variability. So the analytical variability, as I just mentioned, comes from just the sampling and analytical techniques used to analyze each measurement, whereas the total variability is the combination of analytical variability and the environmental variability. So I'm showing 3 different curves here, each corresponding to a different coefficient of variation, or CV, of the measurement method. So a coefficient of variation is essentially the ratio of the arithmetic standard deviation divided by the arithmetic mean. So it's a measure of how precise a measurement technique is. So if a CV is equal to 0.25 or 25%, it is not a very precise measurement because the ratio of the standard deviation to the mean is 25%. So it's not very precise. And techniques such as optical microscopy would have a coefficient of variation of 0.25. On the other extreme, you have a CV of 0.05 or even less than that I'm not showing here, 0.01, meaning there is only 1% variability in the measurements and the analytical precision, that is a very precise method. And most modern measurements for gas chromatography or mass spectrometry analysis of environmental samples would have a CV of 5% or less. Okay, so what does this graph tell us? In most workplace settings and most environmental settings, the geometric standard deviation of environmental variability is somewhere between 1.5 to 3.5. And in this region, if you have a fairly precise measurement, such as these three graphs shown here, then the analytical variability contributes a very small percentage to the total variability. And that's what this graph is showing. So if you have a very precise method now, let's start with a CV of 0.05, and let's say a geometric standard deviation, GSD, of somewhere 2.5. These are typical workplace variabilities. Then, in fact, the analytical variability contributes close to zero for the total variability that you have observed in your measurements. So all the variability comes from the variability in worker exposures. Even if you have a very imprecise method, such as optical microscopy with a CV of 0.25, even there, for the mid-range of GST, somewhere between 2 to 3, 3.5, or even 4, it contributes less than 10% of the total variability. So the analytical variability contributes less than 10% of the total variability. What does this mean? It means that analytical variability is not that important when you are considering the overall variability of exposures for a group of workers. So for typical levels of environmental variability, meaning the geometric standard deviation sigma is greater than 1.5, and for typical values of the coefficient of variance CV, meaning less than 0.15, the contribution of analytical variability, I'm denoting it as I here, is less than 13%. In fact, most modern methods of sample analysis have a coefficient of variation CV less than 0.1, in which case the value of I, that's the contribution of analytical variability to total variability, is less than around 6%. There was a paper published in 1991 by Buring and Lanting that showed that in many occupational settings, the geometric standard deviation sigma has a value roughly around 2.7. But even if you extend that range like I did, even if you extend it to 3, 3.5, and go down to around 1.5, this point still is valid, that the environmental variability is of much greater importance than sampling and analytical variability for exposure assessment. So the key insight from this analysis is that in many instances, it is not cost-effective to use a very precise but expensive analytical method when a less precise and less expensive analytical method is available. Because if we use the less precise analytical method that is also cheaper, we can actually increase our sample size. We can increase the number of samples we obtain, and this will provide a greater overall accuracy and precision in our results. So this is a very important insight. So when you are practicing occupational hygiene or even doing environmental measurements, it's important to increase your sample size. It is not as important to get the most precise, modern, sophisticated method. And that is the key insight I want you to remember going forward in this course.